line and made it right there, and I've taken this line or this expression and put it right there. Does that make sense? These two are ORed together. Either expression can turn on bit 2, but notice this expression will only turn on bit 2 when we're in the bit 1 state. In other words, when we're in the get box state, then we can possibly go to the fill box state. If we're in the fill box state, we can stay in the fill box state. So this is the null transition. Okay? Now, that takes care of B2. Let's unhighlight. Well, I guess I'll leave those highlighted. Let's program bit 3. I'll highlight in a different color, I guess, so we can keep track of these. How do I do that? There. Okay, so I need to program bit 3. Like I said, I would normally ask you guys for input. Please try to follow the pattern and try to think of what I'm going to do next. So I've got to program this expression. So I'm going to need 3 with the same instruction. The first one involves bit 2. Drag and drop. The stop push button is next. And then level. Now I've used level as well, so I can drag and drop that. The last expression for B3 is B3 stop push button procs. So let me copy this. Change it. I'm trying to avoid typing to save time. So B3, stop push button, and the last one is procs. So I'll just copy procs. Paste right. Okay? Does it make sense so far? So I have I've taken these two Boolean algebra expressions and put them in right here. B2, stop, level, all and together, procs, and stop, and full box state B3. Okay? And that's how I'll calculate B3. I have successfully almost. I've almost successfully programmed these 2 bits. There's actually a problem here. I'll show you what it is in just a moment. Okay? It's something that's easy to fix. The last thing to do is to program all the B0 and B1 equations. Let's see, there's a B1 here, and there's a B1 way up here, as well as one more here. Now the number of equations you end up with, depends on the design of your state machine. Don't worry too much about minimizing the number of expressions for the bits. That's not critical. But we have 3 expressions, so we will need, for programming bit 1, we'll need 3 ORs. Okay. The first OR will contain the first equation, which is B0 and start. So B0 and start. B0 is right there. We haven't used the start push button yet. It's I:1/0. Wasn't my camera, was it?
No, sorry.
Sorry. Also trying to not run out of video time. So start push button. The next expression is down here. It's B1 stop push button and not procs. So we need structure like this. We need B1. We need stop push button and not procs. Okay, that takes care of that expression. Finally, for the last B1 equation, we need 2 non-inverting and 1 inverting. So 2 non-inverting, 1 inverting. We need to reference bit 3, the stop push button, and then finally not procs. Okay? And that takes care of programming bit 1. Now we have bit 0, which is the big one. We got 1, 2, 3, 4, 5, 6, 7 expressions for bit 0. Remember Boolean algebra and how there can be simplifications? There will be. In fact, didn't I promise you guys you'd have a lot of time to work on Boolean algebra today? Well, let's push off the homework due date until the end of the day next class. Unless you guys have gotten the Boolean algebra all done. Okay, then we'll push it off.
I almost got it done, but
Almost?
Great way.
Well, usually there's a lot of time with me sitting with each student and going through the equations and showing them where mistakes have been made and simplifications that could have been made and so on. So I want to spend that time with you guys. I don't want to lose that. But you'll see some simplifications here that are pretty neat. Well, if I've got 7 expressions, I'm going to need 7 ORs. 1, 2, 3, 4, 5, 6, oops, that's not what I wanted, 7. The first equation is right here. In fact, I guess I'll turn these equations, I don't know, gray while I'm working on them. So the first expression is B0 equals B0 and not start. So B0 and not start. So there's B0, and there's not start. Now that I've finished that one, let's go to the next one. I'll highlight it. The next expression is B1 not stop, not prox. B1 not stop, not prox. Drag and drop B1 so I don't have to type. Not stop and not prox. And by the way, you can download this code when I'm done with it. It's already on Blackboard except I finished it off before. It'll look almost exactly like this. It's from the same equation, so it should be all right. Okay, next expression, I'm going to highlight over here on the right. It is bit 1, not stop, and prox. So bit 1, not stop, and prox. The next expression, you see a big simplification here. We'll be able to get rid of 3 of these rungs. Finish this off and then you'll see it. The next one is bit 2, not stop, not level. So bit 2, not stop, not level. Bit 2, not stop, and not level. Next expression, bit 2, not stop, level. Okay, bit 2, not stop, level. Bit 2, not stop, level. Well, we got 2 more to go. Working on this one down here. Bit 3, not stop, not prox. Bit 3, not stop, not prox. Okay, bit 3, not stop, not prox. And then finally this expression. Bit 3, not stop, and prox. Bit 3, not stop, prox. Bit 3, not stop, prox. Now, we have successfully programmed the state machine, and it won't do a darn thing yet. Okay? All we've done is play around with a bunch of bits and inputs. We've only taken care of the input side. Now we have to think about the output side. But the output side is trivial. Look, the output side, if you're in the get box state, motor's on, valve's off. It's that simple, right? So we can program that very easily by simply using a bit to reference, for example, the stop state. Let's start there, okay? When in the stop state, what do we need to do? Well, we need to unlatch. Now, here's the only place where we have to worry about latching and unlatching. We have to unlatch both outputs, O:2/0 and O:2/1. Remember that O:2/0 is the motor, and O:2/1 is the valve. Okay? So if we're ever in the stop state, if that's ever true, we're going to turn off the motor and turn off the valve. Well, that was pretty easy. What about when we're in the get box state? Well, when we are in the get box state, we want to latch on the motor and unlatch the valve. Okay, pretty simple. We could set it up as a truth table, and we don't have to do a latch and unlatch. We could do a regular output instruction, but we'd have to set up a truth table where we figure out when is the valve on, when is the motor on, and use logic to figure it out. This is simpler, so we'll just go this way. So my point is there's more than one way to do what I'm doing. But in the interest of time, I'm just going to do it this way quickly. When we're in the fill box state, what needs to happen, in fact, here, let me cheat a little bit. Let me save some time. I'm going to get rid of that last run, copy and paste run below, and I'll just reference another bit. It's going to be the motor and the valve. In the fill box state, I want the motor off, and I want the valve on. See what I did there? Just unlatch the valve and latch the motor. Good. Let's copy the rung, paste the rung below. And so finally, in the full box state, I want the motor to be on, and I want the valve to be off. There we go. This should be an operating state machine. It's still not quite an operating state machine. Let me explain why. Remember that in reality, the PLC evaluates these rungs one by one, right? What's going to happen is it's going to evaluate the stop state. And it might turn the stop state on, but if we're in the get box state, the get box state will also be on. And the logic that depends on the stop state and the get box state will be confused because it'll look like both states are on at the same time. So what we have to do, there's one of two things. We can either make new bits here and then copy them over, but I think what I'm going to do instead is latch and unlatch. In other words, if I calculate that the stop state should be on, I think what I can do is just go ahead and unlatch all the other states at that point. So we'll use a similar technique to what we've got down here, where we will simply latch the stop state and unlatch all the other states, just to make sure all the other ones are off. Does that make sense? So I think we can simply unlatch all the other states. So the other states are box, fill box, and full box. I'll have to set up that same structure on the rest of these, so let me just bear with me while I do it. So we're going to change all these to latches. And I wish I could copy this whole structure, but I don't think I can. Sorry, I'm running into overtime, but I want you to see this work. Let's copy. This left, almost done. Latch. Copy. Paste left, let's just paste left twice. Okay, so I want to unlatch 0, 2, and 3. I'm just turning all the other states off. Turn on the get box state, turn off all the others. Same thing here. Believe it or not, this is a common problem with PLC programming. Most PLC programming, ladder logic programming languages are pretty clunky at editing. Not very good editors. Yeah, that's not what I wanted to do. Let's see, let's just pull that one down here. Unlatch it down here. Let's see. And then the other state is state 1. Okay, so we're going to turn on the fill box, turn off stop, get box, and full box. And so finally, we need to unlatch State 0, 1, and 2. Okay, that should be it. What cardinal rule have I broken?
You have logic on two sides.
No, I haven't saved. I'm living dangerously.
You're shading for this.
Extremely dangerously. Okay. So now let's go to the simulation. The simulator. There's good news and bad news. The good news is if we did everything right, it'll work. The bad news if we messed up is if we messed up in one place, it won't work and it'll be a pain in the butt to find. Okay, that's the bad news. Let's see. Yep, I messed up somewhere.
Did you download it?
Did I download it? Probably not. That's run. I did download it. It should actually begin in, I know what's wrong.
Do we ever call the motor?
Well, yeah, sure, we call the motor, right down here. We turn the motor on when we're in certain states, right? What's happening is we're not beginning in a default state. Notice bit 0, bit 1, bit 2, and bit 3 are all off, right? So I need to somehow turn on bit 0 to get this process started. We have to start the party somehow, okay? Let's go back. Let's add in, let's see, how do I want to do this? I guess I'll add in a rung that says if we are not in any of the other three states, then turn on this bit, okay? So if we're not in state 1, state 2, or state 3, then turn on state 0. That should fix it. There we go. It works, first time. Well, almost first time. It's transitioning between the states very quickly. If we slow it down, you might be able to see it. We're in the get box state, now fill box, full box for a brief moment until the proximity sensor is clear. Now you can look at this and you say, well, why on earth would I want to do this? This seems like a whole lot of trouble. Well, when you try to create your own program from scratch and it's 3 a.m. in the morning and you still can't get the darn thing to work, sometimes this will save you because you can set up a state machine once you're used to doing it with relatively little effort and just make a program that works. It's also fairly bulletproof. We haven't really tested it completely yet. There's one state we haven't tested completely, and that's the stop state. What if I stop and then restart? It works. What if I stop there? That works. Start. Stop during fill. It works. This is common. With a state machine, usually when you stop it at any point and restart it, it works, except, of course, for that. Why didn't it work? I managed to get lucky. I stopped the system where I had a full box. Proximity sensor was true. So it went from the stop state to the get box state. Very quickly, noticed the proximity sensor was true. Went on to the fill box state and started filling the box. By stopping the system, by hitting the stop button, I went to the stop state and destroyed the memory that there's a full box there, you see? Now, if I had an actual operator here operating this machine and he presses the stop button, something's wrong with this box. He's going to clear it. So I'm not worried about that. I'm not worried about that programmatically. I don't think that's a bug in my program, you see. So what he would have done is reset the simulation and then run it again. And then it would work fine. Okay. All right. Quick thing, just one thing really quick. Notice there's a lot of simplifications here. You notice that the conditions here are the same. Get box, not stop, not stop. Here we have prox not true, prox true, and this is an or. That means this actually doesn't matter. It doesn't matter if prox is on or off, this is going to fire. So we can actually eliminate those because it doesn't matter. Similar logic holds here. Fill box, not stop, level true or not true, the signal gets through. that doesn't matter either. Same thing here. Full box, not stop, procs either true or not true, signal gets through. So there's no need for these. What that means is that this row here and this row are redundant. These two are redundant. Well, I'm sorry, let's see, let me make sure I get it right. These two are redundant, these two are redundant, and these two are redundant. So there are three that I can eliminate. So I can simply do this. And I've got the same functionality, well, almost. I've got a conditionless branch there that I don't want. Gonna move things around just a bit. Essentially what I've just done in Boolean algebra is I've factored out one of the inputs. We download this, reset the simulation, download force of habit is safe for that way in Logic Pro, then run. It still works exactly the same way because the logic's exactly the same. I just factored out an expression. Okay. Sorry I went into overtime. That's it. So now you've seen state machines being made. I know they look scary. They're kind of a last resort because it is a lot of work. You probably will not try to use a state machine initially in your elevator program for the project, but this is the last topic. This is the last thing I have to teach you about PLCs before I will ask you guys to start the project. So as soon as you're done with the next homework, then the project is what's on our plate. I will, of course, help you with it. If you say, hey, I'd really like to use a state machine because I think it'll solve this problem, it's a tough problem, but I'm not sure exactly how to do it, I'll walk with you through that. I'll help you create the state transition diagram and figure out how to make it work, okay? There are actually programs to help you create state machines. I don't have any of them, and I want you to create them by hand so that you learn how they work in any case for the project. Questions, comments? You guys still alive?
Well,
Okay, good. All right, well, we'll see you guys next week then.